As we gaze up at the night sky, we often take for granted the seemingly stable dance of our planet and its loyal satellite. But what if I told you that the moon's gentle orbit is actually a slow-motion heist, stealing our rotation speed and changing the very fabric of our day? Now, you might think the moon's orbit is a fixed, predictable path, but there's a surprising truth about its relationship with our planet. The moon's tidal lock, a phenomenon where one side of the moon constantly faces the Earth, is a result of the gravitational dance between our two celestial bodies. That number sounds absurd until you realize the moon is moving away from us at a rate of about 3.8 centimeters per year. Yes, you read that right. The moon is slowly increasing its distance from the Earth, and with it, its influence on our planet's rotation speed. But here's the kicker: as the moon pulls away, it's actually stealing some of the Earth's precious rotation speed. The implications of this are still unclear, but one thing is certain: our planet's very rhythm is being subtly altered by the moon's gradual retreat. The Earth's rotation is slowing down, but what does that actually mean for us? At first glance, it's a tiny change, just 1.78 milliseconds per day. That number sounds absurd until you realize it adds up over centuries. Think of it as a slow bleed, where the Earth's rotation loses a few minutes every 100 years. It's a subtle shift, but one that's already being felt. The reason for this slowdown is due to the moon's gravitational pull, which is slowly increasing the length of our day. But here's the thing: the moon's influence isn't just a simple tug-of-war. It's a complex interplay of forces that's been shaping our planet's rotation for billions of years. And yet, despite this subtle yet significant change, we're still debating the full implications. What does it mean for our climate, our oceans, our very way of life? The answer, much like the Earth's rotation, is slow in coming. But one thing's for sure: as our planet's rotation slows, so too does our sense of control over it. Let's take a look at the moons of other planets. It's worth noting that the moon's behavior is quite unique among them. Take Jupiter's moon, Europa, for example. It's tidally locked, meaning it always shows the same face to its parent planet, just like our own moon. However, that's where the similarity ends. Europa's orbital speed is a fraction of our moon's, and it's not slowly drifting away from Jupiter like our moon is from Earth. That number sounds absurd until you realize that it's because of Jupiter's much stronger gravitational pull. But here's the interesting part: some of these moons are actually moving away from their parent planets, but not at the same rate as our moon. So, what's going on here? Is it a matter of planetary mass, or is there something more fundamental at play? We still don't have a clear answer to that question, and it's worth exploring why our moon's behavior is so different from the rest. The moon's gravitational pull is often misunderstood as a gentle, benevolent force that stabilizes our planet's axis. But the truth is, it's a force to be reckoned with. Let's take a closer look at just how strong it is. The moon's mass is about 1/4 of the Earth's, yet it exerts a pull on our oceans that's roughly twice as strong as the sun's. That number sounds absurd until you realize that it's not about the size of the object, but about its proximity to us. The moon is a mere 239,000 miles away, which is relatively close in astronomical terms. That proximity is what gives it such a significant influence on our tides and, as we'll explore later, our planet's rotation. But here's the thing: the moon's gravity is also slowing down the Earth's rotation, causing our days to lengthen by about 1.8 milliseconds every century. That may not sound like much, but it adds up over time, and it's a reminder that the Earth-Moon system is still evolving, still changing in ways that we're only just beginning to understand. Earth's axial tilt is a fundamental aspect of our planet's behavior, but it's often overlooked in discussions about the moon's influence. That's because the tilt itself isn't directly affected by the moon's orbit, but rather it's a product of Earth's internal dynamics. However, the moon's gravitational pull does have a subtle impact on the tilt's stability. That number sounds absurd until you realize it's a difference of just a few hundredths of a degree over millions of years. It's a tiny effect, but it's enough to make me wonder, what other subtle influences are at play here? The moon's orbit is slowly increasing in size, which means its gravitational pull on Earth's oceans is also changing. But how does this relate to the tilt, and what does it mean for our planet's rotation speed? The moon's escape velocity is a critical point for Earth's rotation, and it's not as straightforward as it sounds. That's because the moon is slowly drifting away from our planet, and with it, it's also taking some of Earth's precious rotation speed. Now, a 3.8 centimeter per year increase might seem like a tiny margin, but it's enough to have a significant impact over millions of years. That number sounds absurd until you realize that it's been happening for so long that it's essentially irreversible. The moon's gravity is what keeps our oceans in sync with the Earth's rotation, and if it continues to slip away, we might start to see some interesting consequences. But here's the thing, we're not entirely sure what the long-term effects will be. Some scientists argue that the moon's increasing distance will slow down our rotation, while others claim it will actually speed it up. The debate's ongoing, and it's clear that there's still a lot we don't know about the moon's influence on our planet. So, what does this mean for Earth's rotation in the grand scheme of things? Will we see a gradual slowdown or a catastrophic acceleration? The answer, for now, remains shrouded in uncertainty. The tidal lock, where the moon's gravitational pull slows Earth's rotation, is often seen as a straightforward consequence of orbital mechanics. But what if I told you there's a dark side to this story? A side that challenges our understanding of the moon's influence on our planet. The tidal lock's effect on Earth's rotation speed is a loss of about 1.8 milliseconds per century. That number sounds absurd until you realize the cumulative impact over millions of years. The moon's steady creep away from Earth, a process called lunar recession, is stealing our rotation speed. It's as if the moon is slowly draining our planet's vitality. But here's the thing, we're not entirely sure how this affects our planet's core. Does it lead to changes in the Earth's magnetic field? Could it even impact our climate? These questions linger, casting a shadow over our understanding of the tidal lock's true nature. At first glance, the moon's slowdown might seem like a minor perturbation in the grand scheme of celestial mechanics. But that number, about 1.5 inches every year, sounds absurd until you realize what it means. It's not just a matter of the moon drifting further away from us, but also of how it affects our planet's rotation speed. The Earth's day used to be shorter, but as the moon slowed down, our planet's rotation began to slow down too. That's a significant change, and one that's been happening for billions of years. The implications are far-reaching. A slower Earth means a longer day, which in turn affects the tides, the climate, and even the way our planet's interior behaves. It's a subtle change, but one that's been happening for so long that we've barely noticed. Or have we? What else have we misunderstood about the moon's influence on our planet? The Earth's core, a massive ball of iron and nickel, is often cited as a primary driver of the moon's slowdown. But how exactly does it manage to exert such a profound influence? That number sounds absurd until you realize the Earth's core is about the size of the moon itself. To put it simply, the core's gravitational pull is what maintains the moon's stable orbit, and as the core's magnetic field weakens, the gravitational pull lessens. This subtle change has a profound effect on the moon's velocity, causing it to gradually slow down. But here's the thing, we're still not entirely sure what's causing the core's magnetic field to weaken in the first place. Is it a result of changes in the Earth's interior, or is it something more complex, like the effects of the solar wind? Whatever the reason, the fact remains that the Earth's core is quietly orchestrating the moon's slowdown, a phenomenon that has profound implications for our understanding of the Earth-Moon system. The notion that the sun's influence affects the moon's orbit has led many to speculate about its role in the moon's increasing distance from Earth. But let's separate fact from fiction here. The sun's gravitational pull on the Earth-Moon system is indeed significant, but it's not the primary driver of the moon's recession. That distinction belongs to the tidal interactions between Earth and Moon. Yes, the sun's gravitational force does have a minor impact on the tidal bulges, but it's a mere 20% of the total effect. That number sounds absurd until you realize that it's a cumulative effect over millions of years. The sun's influence is more about the timing of these tidal interactions, not their overall magnitude. But here's the thing, the exact timing and extent of this influence are still a subject of debate among researchers. What does this mean for our understanding of the moon's orbit? Does it challenge our current models, or does it simply refine them? The formation of the moon is a tale of catastrophic events and cosmic upheaval. One theory suggests it was born from a massive collision between Earth and a Mars-sized object, the debris from which coalesced into our lunar companion. But here's the thing. This collision would have released an unfathomable amount of energy, enough to reorganize the very fabric of our planet. And yet, we're told this event had a relatively minor impact on Earth's rotation. That number sounds absurd until you realize it's actually a crucial clue to the moon's future behavior. If the collision was indeed the moon's genesis, it should have had a profound effect on its orbit. But as we'll see, the moon's slow drift away from us is not what you'd expect from a body forged in such a cataclysmic event. The question is, what does this say about the moon's true nature, and what does it portend for our planet's future? The moon's slowdown, as we've established, has a profound impact on our planet's rotation. But how does this translate to the Earth's climate patterns? That's where things get interesting. The Earth's rotation, or more specifically, the rate at which it rotates on its axis, is what gives us our day-night cycle. As the moon slows down, the Earth's rotation speed begins to increase. But here's the catch. This increase in rotation speed comes at the cost of the Earth's rotational angular momentum. That number sounds absurd until you realize what it means. The Earth's axis is slowly wobbling, causing our poles to shift slightly over time. This, in turn, affects the distribution of solar energy across the planet. Some argue that this shift could lead to more extreme climate patterns, while others claim it's still within the realm of natural variability. What's clear, however, is that the moon's slowdown is yet another piece in the complex puzzle of our planet's climate dynamics. And yet, we still don't fully understand the extent to which this phenomenon will impact our climate. Will it exacerbate the effects of global warming, or is it a separate issue altogether? The uncertainty is palpable, and it's precisely this uncertainty that makes the moon's slowdown so fascinating. The Earth's rotation is a finely tuned machine with a 24-hour day that's been a constant for our species. But scratch beneath the surface, and you'll find a web of anomalies that defy explanation. Take the length of a day, for instance. It's not fixed, but slowly increasing by about 1.78 milliseconds every century. That number sounds absurd until you realize it adds up to nearly 2 hours over the course of 620 million years. What's driving this change? The moon, it turns out, is slowly moving away from us at a rate of about 3.8 centimeters per year. That's right. The same moon we've been watching wax and wane for millennia is now essentially stealing our rotation speed. But here's the kicker. This process started around 620 million years ago, during a period known as the Great Unconformity. The question is, what triggered this sudden acceleration? Was it a massive asteroid impact, or perhaps a change in the Earth's core? The truth is, we still don't know, and the mystery only deepens when you consider the moon's own tidal interactions with our oceans. The more we learn, the more we realize how little we understand about our own planet's inner workings. The moon's orbital period, that's how long it takes to complete one orbit around the Earth, has been slowly increasing over the past 620 million years. That number sounds absurd until you realize it's been happening for so long, it's almost imperceptible. But it's not just a trivial change. The moon's tidal interactions with the Earth are responsible for this slowdown. As the moon moves away, it's also slowing down our planet's rotation. That's right. The very thing that keeps our days relatively constant is being sapped away by the moon's steady retreat. This has significant implications for our planet's geological activity, particularly earthquakes and volcanic eruptions. The question is, will we ever notice the effects of this subtle theft? Or will we be too caught up in our own problems to care? The notion that the moon is slowly drifting away from our planet might seem like a minor detail, but its consequences are far from negligible. A slow rotating Earth would have a profound impact on our daily lives, even if it's not immediately apparent. That number sounds absurd until you realize that a 1-second discrepancy in the Earth's rotation per century might not seem like much, but it adds up over time. What does it mean to have a day that's, in effect, 1.78 milliseconds longer? The simple answer is that our clocks would be out of sync with the Earth's rotation, requiring us to adjust our timekeeping. But the implications go far beyond just keeping accurate time. As our planet's rotation slows, it would also affect the distribution of time zones around the world. Some regions might find themselves in a perpetual state of daylight saving time, while others would experience the opposite. The consequences of a slow rotating Earth would be a constant reminder that even the most seemingly trivial aspects of our lives are inextricably linked to the celestial bodies that govern our existence. Join me as we delve into the intricacies of the moon's orbit and its impact on our planet's rotation. What we uncover will challenge your understanding of the cosmos and leave you wondering about the unseen forces that shape our world.